Morbidity. There are two basic measures of disease occurrence in populations: incidence and prevalence. Incidence measures the occurrence of new disease, and prevalence measures the existence of current disease. There are two kinds of incidence: cumulative incidence and incidence rate. Cumulative incidence is a proportion without units and ranges from 0 to 1. Incidence rate is a true rate with units of 1 over time and ranges from 0 to infinity. The denominator is person time at risk. Note that the attack rate is not actually a rate, but rather a proportion or form of cumulative incidence used for short-term diseases, such as infectious disease and outbreak investigations. For example, if 100 people attend a party and 30 get diarrhea within 24 hours, the attack rate is 30%. But this is really a proportion, not a rate. Incidence is the rate at which new events occur in a population in a defined period of time. Events can be a disease episode, or in what is referred to as mortality rate, the event is death. The key concept is a change in status from healthy to sick over a period of time. In the numerator, you have the total number of new events. In the denominator, you have the total number of subjects or population at risk. And the period of time during which the cases accrue can be a year or any other time. The three key ideas are: 1, that incidence measures new disease events or cases. And 2, that new cases are measured in a candidate population of people at risk of getting the disease. For example, if the event of interest is uterine cancer, then the candidate population should not include women who have had hysterectomies. The denominator should also exclude people who have already developed the disease because they cannot be new cases. And 3, incidence takes into account the specific amount of time that the population is followed until they develop the disease. Cumulative incidence is best used in fixed populations when there are no or small losses to follow-up. When the assumption that everyone in the population has been followed for the specified time period is broken, then incidence rate can be used to examine the actual time period of risk for each person, from the beginning of the period to the time the disease is detected, or if the person does not become sick until the end of the observation period. This is a true rate and best suited for open or dynamic populations or cohorts. Similar to cumulative incidence, the numerator is the number of new cases, but unlike cumulative incidence, the denominator is given in units of person time. Person time is a measure used when members of a population or study group are under observation for different lengths of time. Each person is observed from an established starting time until one of 4 endpoints is reached: the onset of disease, death, migration out of the study, or we call loss to follow-up, or the end of the study. Consider these two examples. One person followed for 5 years without developing disease is said to contribute 5 person years of follow-up. Another person followed for 3 years before being lost to follow-up is said to contribute 3 person years. Person time is epidemiologic jargon. To convert this jargon to something understandable, simply replace person years with persons per year. So for example, reporting the results as 2.5 new cases of heart disease per 1,000 persons per year sounds a bit more like English than jargon. Person time also assumes that the probability of disease during the study period is constant, so that 10 persons followed for 1 year equals 1 person followed for 10 years. However, the risk of many chronic diseases increases with age, so this assumption is often not valid. Participants do not have to begin at the same time. Taking this example here, one participant could start in 1994 and be followed until 2004 and contribute 10 person years. Also, while it is ideal to calculate person time on an individual basis, this is time consuming and labor intensive in large studies. Thus, shortcuts such as using the average follow-up time may be used. Consider this example. Here we have 5 participants added to the study. All began in 1990, and you can see that the first person contributed 3 years, the second 13, the third person contributed 7 years, the fourth person contributed 16 years, the fifth person contributed 9 years, to give a total of 48 person years. Here's another example of incidence rate of heart attacks observed over a 10-year period, although not all students were observed for the entire 10 years. As can be seen from the table, 10 students were observed only for 9 years, 7 students only for 8 years, 2 students for 7 years, and 1 student for only 1 year. Multiplying the number of students by length of time observed, or column A by column B, gives the right-hand column and a total of 461 person years. If 5 heart attacks were observed during that period, the incidence rate of heart attacks would be 5 over 461 times 100, or 1.08 per 100 person years. For rare diseases, incident rates are usually reported in 100,000 person years. Cumulative incidence and incidence rate focus on measuring the transition from health to disease. These measures have complementary strengths and weaknesses. Cumulative incidence is easy to calculate and understand, although it is less accurate when assumptions, such as a fixed population, are not met. Although incidence rate has greater accuracy, especially in dynamic populations, its person-time denominator is more difficult to calculate and understand. While both measures of incidence measure the frequency with which new disease develops, prevalence measures the frequency of existing disease in a population. Prevalence is the number of existing cases in a population divided by the total number of people in that population at a specified time in the case of point prevalence, or over a specified time period in the case of period prevalence. It is a proportion. All individuals included in the numerator are also included in the denominator. All persons in the population do not necessarily need to be at risk of becoming a case. It is a measure of the burden of a disease in a population, and it is useful for estimating frequency of exposure or disease and studying risk factors that lead to chronic cases. Because it measures burden, it is useful for determining allocation of health resources. However, it is important to note that high prevalence does not imply high individual risk for disease. Rare diseases that have long duration may have higher prevalence, but still relatively low incidence or risk. Differential survival also affects prevalence. For example, diseases of short duration, due to death or recovery, lead to lower prevalence estimates, for example, pancreatic cancer. Diseases of longer duration lead to higher prevalence estimates, for example, HIV/AIDS. In the case of point prevalence, the question we're interested in is, do you currently have disease X? This could be shown by the example of prevalence of diarrhea in children in a village on a particular day. July 13th was 33%, for example. With period prevalence, the question is, during a particular time interval, some of those cases may be new cases at some point in the interval. The question is, have you had disease X in the past 10 years? An example would be prevalence of all cancers in women in 2008 or in a particular time period. Here are a couple examples of prevalence. Point prevalence, you have 500 men with lung cancer were asked about their smoking habits. 461 men smoked at least 1 pack of cigarettes per day. What is the prevalence of smoking in this group of men? Prevalence equals 461 divided by 500 to give a prevalence rate of 92.2%. Period prevalence, the prevalence of bird flu among UD students in the fall 2020 semester between the dates of September 1st, 2020 and December 15th, 2020, we can calculate. And here, because it has a proportion, it has no units, the prevalence can be multiplied by a fixed number to express the number of cases for a given population size. So in this example, we have 569 cases of bird flu for 18,634 UD students, but we're interested in expressing this in terms of 10,000 UD students. So we multiply 569 by 10,000 and solve for x, which is multiplied by 18,634, and x is equal to 305.36 cases per 10,000 UD students. One example of prevalence is the BRFSS maps of obesity prevalence by state. This is the Behavioral Risk Factor Surveillance System, and it's the nation's premier system of health-related telephone surveys that collects state data about U.S. residents regarding their health-related risk behaviors, chronic health conditions, and use of preventive services. These maps show state-by-state obesity prevalence, or the percent of the population that had a BMI greater than or equal to 30. You can see that in 1990, up in the upper left, no state had more than 14% of the population with BMI of greater or equal to 30. By 1995, many states had 15 to 19% of their population considered to be obese, and no state had an obesity prevalence of less than 10%. By 2005, several states had an obesity prevalence of over 30%, while only a few states had an obesity prevalence of 15 to 19%. There are many factors that influence prevalence. For example, factors that influence prevalence and increase prevalence are longer duration of disease, prolonged life of patients without cure, increased incidence, in-migration of cases, out-migration of healthy people, in-migration of susceptible people, and improved diagnostic procedures. Prevalence can be decreased by shorter duration of disease, high case fatality rate from disease, decreased incidence, out-migration of cases, in-migration of healthy people, or improved cure rate of cases. This graphic may be helpful to understand the relationship between incidence and prevalence. Prevalence is affected by incidence as well as by deaths and cures. Incidence is like the inflow, and deaths and cures are the outflow of the affected population, the prevalence. Prevalence refers to the proportion of persons who have a condition at or during a particular time period, whereas incidence refers to the proportion or rate of persons who develop a condition during a particular time period. If the duration of disease is short and incidence is high, the point prevalence becomes similar to incidence. So when D is short, I is high, P is roughly equal to I, incidence. If the duration of disease is long but incidence is low, then prevalence increases relative to incidence. So the numerator for prevalence includes all persons ill from a specified cause during the specified interval, regardless of when the illness began. High prevalence of a disease within a population might reflect high incidence or prolonged survival without cure, or both. Low prevalence might indicate low incidence, a rapidly fatal process, or rapid recovery. Let's look at the example of AIDS. The prevalence of AIDS has increased steadily over time. In the early 1980s to 1990s, prevalence of AIDS increased because AIDS case definition expanded and because incidence increased. Thus, prevalence increased because inflow into the diseased population increased. Since the mid-1990s, prevalence increased because improvements in treatment resulted in dramatic reductions in the number of AIDS deaths. Thus, since the mid-1990s, prevalence increased because outflow decreased. In fact, prevalence increased despite stable incidence during this period.